What is the best approach for transient radiation analysis in engineering? Imagine trying to catch a fleeting shadow or a sudden burst of light that changes in an instant. That's what transient radiation analysis is all about. It's about understanding how radiation behaves when conditions change quickly. In engineering, this is vital for designing systems that can handle rapid heat transfer events. Think about laser heating, glass manufacturing, or thermal protection systems that experience sudden temperature shifts. To get accurate results, engineers need to solve the transient radiative transfer equation. This equation describes how radiation intensity varies over space, time, direction, and wavelength. Because it's complex and often nonlinear, analytical solutions are rare. Instead, numerical methods are used. One common approach is the discrete transfer method, which breaks down the angular domain into small segments and calculates radiation along discrete rays. This method is efficient and works well for time-dependent problems. Another popular technique is the finite element method, which divides the physical space into small elements and solves the equations over time. Combining these with mixed explicit-implicit time integration schemes helps balance accuracy and computational load. Explicit methods are simple but requiring small time steps, while implicit methods are stable for larger steps but more computationally intensive. Often, a mix of both is used for better efficiency. Boundary conditions are also key. Radiation boundary conditions can be nonlinear and need to be coupled with conduction and convection heat transfer for realistic modeling. For example, inside a glass sheet, radiation interacts with heat conduction, affecting the overall temperature distribution. The optical properties of the medium, like absorption and scattering coefficients, influence how radiation travels and how long it takes to reach certain areas. Accurate modeling of these properties is essential for reliable results. Validation is important too. Numerical results should be checked against experimental data or known analytical solutions whenever possible. This approach is used in many applications, from laser heating of materials to transient thermal shielding in aerospace. For complex three-dimensional geometries or media with scattering, methods like the transient radiation element method or the discrete ordinates method combined with finite element spatial discretization are effective. In the end, the best approach combines a solid mathematical model with efficient numerical techniques for both time and space. It also couples radiation with conduction and boundary conditions relevant to the specific problem. This way, engineers can accurately simulate how radiation behaves over time, helping them design safer, more efficient systems.